Let us talk about the structure of the atom, or modern atomic theory as we know it today. And let's study the brief history of how we arrived at the modern atomic theory. As early as 400 BC, we had two philosophers, Leucippus and Democritus, that devised that matter was made up of atoms, or tiny indestructible particles. But it wasn't about 2,000 years later, till 1808, that we had Dalton come in. And Dalton said that he formulated a theory based on Leucippus and Democritus. And his first part of the theory was that exactly what Leucippus and Democritus said, was that each element is made up of tiny indestructible particles, and these atoms are unique to each element. So the chlorine atom will have unique atoms that are different than the fluorine atom, which would be different than the oxygen atom, for example. And that these atoms can combine in simple whole number ratios to form compounds. Well, then we had Thomson come in, and Thomson discovered the parts of atoms. And so he said atoms can be further divided, and he discovered something called the electron, which is a negatively charged particle that is distributed in a positively charged sphere. So this is a positively charged sphere that you imagine as the atom, and the negative charge was dispersed throughout in what he called the plum pudding model. Well, his student Rutherford came in, and he wanted to prove Thomson's plum pudding model correct. So he shot very dense alpha particles, which were much more massive than the electrons, and he shot them through a thin gold foil. And so he said, well, if we had the plum pudding model, then the alpha particles, since they're positively charged and very dense, should go straight through. But what he ended up finding was, most did go straight through, but he ended up getting some deflections at certain angles. And he said, okay, that's strange. So that must mean that the atom is mostly empty space, but it has a very dense nucleus in the middle that is positively charged. And this will account for why most of the alpha particles went straight through, but some, when they came across the dense nucleus, they actually deflected back. And so that is how we arrived at the modern atomic theory. And we know that the nucleus makes up actually 99.9% of the mass of the atom, so it's very dense. And we added later to this that it doesn't only have positive protons in it, it also has neutral neutrons, and we call those neutrons because they're neutral. They're massive, but they do not carry any charge. And the electrons are negatively charged, and they're dispersed throughout the rest of the atom. And they're actually very light. They don't give too much to the mass of the atom. And so we found out, in summary, that protons are positive 1 charged, neutrons are 0 charged, electrons have a negative 1 charge. And we found that we have their mass in kilograms, but chemists don't use too much of kilograms, so we need something, because we're working usually with very small numbers, so we need something more easier for us to comprehend. So we came up with a standard of AMU, so the proton is 1 AMU. The electron is also approximately 1 AMU. And the electron is very, very small, so you can say it has 0 AMU because in comparison to the neutrons and protons, it's actually its mass is actually negligible and doesn't give too much towards the mass of the whole atom. So the atomic mass unit, AMU, is defined as 1/12 of the mass of a carbon atom containing 6 protons and 6 neutrons. And that is just the standard. Okay, so we've talked about the structure of the atom. We've talked about electrons, neutrons, and protons. Now let's do a conceptual checkpoint to make sure we have everything in check. An atom composed of which of these particles would have a mass of approximately 12 AMU and be charge neutral? So it has to have a mass of 12 AMU and be charge neutral, or 0 charge, right? So here, let's do, for A, we have 6 protons and 6 electrons. In regards to charge, we will have 6 times +1 charge, because each proton is +1 charge. And then we will have 6 times -1 charge. So 6, +6 plus -6 is 0. So there you go, that's charge neutral. But what is its mass? In terms of mass, let's see what we got. We have 6 protons at 1 AMU each, plus 6 electrons, but electrons, remember, have 0 mass. They can be considered negligible for our purposes. So that would leave us with 6 AMU only. So that cannot be right. So let us do the next one. Here we have 3 protons. So let's do the charge first. So 3 times +1. We have 3 neutrons, but remember, neutrons are neutral in charge, so they have 0. And we have 6 electrons, which are each negatively charged. So let's see then. We have 3 plus 0 minus 6, which will give us a -3 charge, right? So that cannot be right. But let's do the mass for that as well to see. So the mass is 3 times 1 AMU, because we have 3 protons and 3 neutrons, which are also 1 AMU, and we have 6 electrons, which are 0. So that will give us 6 AMU. So that is not correct in both conditions that we want. For C, we have the charge. We have 6 protons, 6 times +1 charge, times 6 neutrons times 0 charge, and we have 6 electrons, which are times -1 charge. So what's that going to be? 6 plus 0 minus 6 is 0. So that meets one of our conditions. Now let's do the mass. For mass, we have 6 times 1 AMU, because each proton is 1 AMU. And then we have 6 neutrons, which are also 1 AMU each. And then we have 6 electrons that are approximately 0. So 6 plus 6 is 12 AMU. So it looks like we got both of those in check. So it would seem our answer is C. But let us do this D problem just for fun to see the difference. And so in D we have the charge being 12 times 0, because 12 neutrons that are 0 charged, plus 12 electrons that are -1 charged. So you're going to have -12 for your charge, something that you'll never see in chemistry. And we'll explain why that is later in the chapter. So for mass, we have 12 neutrons that are 1 AMU each, and we have 12 electrons that are about 0 AMU. So that meets our condition of 12 AMU. So this will just verify that C is the correct answer.